Welcome back to the philosophy section of Logic, Language and Information. We're looking at vagueness and the Sorites paradox. We've got an argument which seems to be valid, which leads from premises which seem true to a conclusion that seems false. These seemings can't all be right. In this lesson, we'll look at the way out that rejects the validity of the argument. This is one of the four options in response to the Sorites paradox. The second option, according to which logic does apply, but the Sorites argument isn't valid. This will involve revising or expanding the picture of logic we've painted so far in the subject, because our traditional two-valued picture takes the Sorites argument to be valid. We'll explore an approach from Jan Łukasz, the Polish logician famous for many-valued logics, and in particular, a logic we now know as fuzzy logic. One way to picture this is to think of a gap between the values of 0 and 1. And we can think of there being a range of truth values in between 0 and 1, in particular, a truth value that we might call a half. This is an intermediate truth value, and you can think of it as a truth value suspended halfway in between truth and falsity. It makes sense to think of borderline cases between definite truth and definite falsity as taking this intermediate truth value. So let's see our truth tables and think about how we might expand the picture to include this new truth value. The conservative choice is to take the original Boolean two values as they were before. Now for negation, if p has the value a half, it makes sense to think of not p as having a value a half too, since if p is intermediate between truth and falsity, then not p seems to be just as intermediate between falsity and truth. So we'll give not p the value a half when p has the value half. Now, let's consider conjunction. I've written this in a square table with rows and columns. The rows are labelled with the first conjunct and the columns with the second. So the bottom left 0 in the table here indicates that a conjunction of a true thing with a false thing is false. This is just a new way of presenting the truth tables that we've seen before, which takes up less space, which is important because we're going to have 9 options. So when you add in the half values as other possible values, it makes sense to say that if we can join anything with a false thing, the result is false. So we'll put zeros in those two slots there. Next, it makes sense to say that if you can join a true thing with a second thing, then the value is whatever that second thing has, because the other conjunct is as true as it needs to be for the conjunction. So that fills in these two values of a half here in the table. And this leaves the middle spot. A half conjoined with a half should just take the value a half. And this is Łukaszewicz's truth table for conjunction, now with the three values of 0, 1 and a half. Disjunction is similar. Anything disjoined with a true thing is true. Anything disjoined with a false thing has the same value as that other disjunct, and a half disjoined with a half is a half. The conditional table is a little bit more complicated. A conditional with a false antecedent is true, and one with a true consequent is true. So that's the outline of the table here. Now, a conditional with a true antecedent, that's the bottom row, has the truth value of its consequent. So 1 implies a half is a half. And a conditional with a false consequent, that's the left column, has the negation of the value of its antecedent. So a half implies 0 is a negation of a half, which is a half. And this leaves the middle value here. A half implies a half. And Łukaszewicz's choice for this value is 1. Take a borderline case of red. It seems like the statement, if this is red, it's red, should be true, even if the idea that it's red is intermediate between truth and falsity. So these are the tables for Łukaszewicz's three-valued logic. The practice exercises for this section will have you looking at the way that these three-valued tables work. Now, a three-valued logic like this is a good start at allowing for gaps between truth and falsity, but it's not the only option for modelling vagueness. Friends of more than 2 truth values pursue the option of more truth values than 3. In fact, they pursue many more. We could think of truth as seriously coming in degrees, with 0, say, at the bottom and 1 at the top, and not just the value halfway between, but values for all of the numbers between 0 and a half. Because after all, if redness comes in degrees, shading evenly and smoothly between the red and the non-red, truth might come in degrees too, where the degree to which something is red rises or falls in sync with the degree to which the claim that it's red is true. And we can then explore the interaction between these truth degrees in the connectives. I'm not going to draw all of the truth tables because I'll have many more entries, but it's straightforward to explain the general principles. Negation flips truth values, so if you interpret not A, that has 1 minus the value of whatever you interpret A as. So if A has a value up here, then not A is going to have a value down there. For conjunction, if I had B somewhere along this set of degrees, then the conjunction A and B should take the minimum of the two values of A and B, whereas the disjunction A or B should take the maximum of the two values. Now, conditionals, again, are a little bit more complicated. If I've got a conditional and the consequent of the conditional, say B, is above A, if it's at least as true as the value that the antecedent has, then Łukasiewicz's rule is that the whole conditional is true, because if something down here counts as true, so does something which is truer than it. Otherwise, if the consequent of the conditional drops below the antecedent, and here the gap between the consequent and the antecedent is some height, then Łukasiewicz's rule is that the whole conditional drops exactly that far from the total level of truth, which is true. So the rule for this is that if the interpretation of the antecedent is above the interpretation of the consequent, then the whole conditional gets 1, and then you drop the value of A below 1, and then you add back the value of B, and that gives this interpretation. So if you check these rules and pay attention to only 0, a half, and 1, you'll actually see that you'll get Łukasiewicz's 3-value truth tables back. Now these are the truth tables of Łukasiewicz's infinitely valued logic, where you've got an infinity of truth values shading evenly between truth and falsity. Now here's a question for you to try. Here are 3 circles which are numbered 1, 2, and 3. And let Ri be the statement circle number I is red, and let Li be the statement circle number I is large. Now let's suppose that L1 and R3 are true, since circle 1 is large and circle 3 is red. And let's suppose that L2 and R2 are a half, because circle 2, at least on my screen, is a borderline case of red and it's a borderline case of large. Finally, L3 and R1 are false. They get the value 0, since circle 3 is large and circle 1 isn't red, it's orange. Now, which of the following statements on the screen are true? Which of them get the value 1? How did you go? If you've got questions or comments, or if you'd like to explore these issues further, take a look at the course notes for this section and head in the discussion boards to follow things up. I'll take a look and see how you're all going. Now, in the setting of Łukasiewicz's infinitely valued logic, we should ask the question about when an argument is valid, because our aim is to show that the Sorites argument is actually invalid. But what does validity mean here? Now, the general idea of validity is the truth transfer from premises to conclusion. But now, what do we need in a truth transfer? What counts as true enough? We can't really tell, because we've got lots of different ways that things could be true to different degrees. So our definition of validity actually has a sliding scale, just in the same way the truth has a sliding scale. Given a threshold value for truth, say up at level t, an argument from premises to conclusion is t valid if whenever the premises are above t, so is the conclusion. You can think of t validity as meeting the threshold of truth. You think of t as the threshold to count as true. Now we'll indicate t validity with a turnstile with a subscript t here on the screen. Now if an argument is t valued for absolutely all of the threshold values between 0 and 1, we call it absolutely valid. And an argument is absolutely valid whenever the conclusion is higher than the minimum value of its premises. Here's an example of an argument which is going to turn out to be valid. To show that it's valid, we'll suppose that the value of the premise is above the threshold t, and we want to show that the conclusion is also above that threshold value. And in getting to this conclusion, we'll look at two different cases. If the value of p is under or equal to the value of q, then the Łukasiewicz's rule for the conditional says that p implies q gets the value 1. And in that case, p implies q gets exactly whatever value q gets. So, because the value of p is less than or equal to the value of q, the value of the conclusion of the argument is indeed greater than or equal to t, because the value of p is greater than or equal to t. So that's the first case done. On the other hand, if the interpretation of p is not less than or equal to, but rather greater than the interpretation of q, then this conditional here has the following value, and I'll just write it out. It is 1 minus, now the value of p implies q, is 1 minus the value of p plus the value of q, and we've minused that, and we've added the value of q, because now that's the consequent of this whole conditional. And I'll just look at this value and unpack it. That's 1 minus 1 plus the value of p minus the value of q plus the value of q, and the 1's cancel out, and the minus the value of q and the minus of the value of q cancel out, and you've got the value of p. And so the conclusion of the argument now, in this case, has just the same value as the premise. And so if the premise is above the threshold value, so is the conclusion. So in either case, we've got that this is a valid argument. The conclusion is always above the threshold value if the premise is. So this is an example of an argument which is invalid. Sorry, this is an example of an argument which is valid. We're going to look at the Sorites argument, which is hopefully an example of an argument which is invalid, because that's what we were after. So let's look at the Sorites argument in a simplified case here, where I've actually only got 4 premises, and we'll actually only make 4 divisions in the strip. So let this be patch 1, this be patch 2, this be patch 3, and patch 4 somewhere over here, which is clearly orange and not red. And let's the value of R1, let that be given the value true. And R2, let that thing have the value of 80%, because this is, although it's looking a bit sort of orangey pinky, at least on my screen, it's still red to a high degree. And let R3 get the value 60%. And let R4 get the value 40%. Maybe you'd give them different truth values, it doesn't really matter. You could choose different examples of patches along the screen. In this instance of this argument form, the conditional premises will all be 80% true, because we go from 100% to 80%, and the gap, the drop from truth to falsity, from antecedent to consequent, is a 20% drop. And so the whole conditional here has a truth value of 80%. And again, as I go from 80% to 60%, it's a 20% drop, so this is an 80% conditional. And again, the last premise is also, in this case, going from 60 to 40. So it's a 20% drop. The conditional is 80% true. The first premise we chose to be 100% true. So each of the premises meets the 80% threshold. But look at the conclusion. The conclusion is only 40% true on this view. It follows that the argument is invalid. The premises are truer than the conclusion. And the argument is invalid because the errors in the premises accumulate. They combine to make a conclusion which is much falser than any of the premises were. This is how the fuzzy logic analysis tells us what's gone wrong in the Sorites paradox. The argument is invalid because the premises in a long Sorites argument are true to an extraordinarily high degree, but the conclusion is not. The conclusion is false to a very, very high degree. Now, this is one way out of the paradox. And the result is a very interesting and fruitful picture beyond the assumption of two truth values. But questions remain. I've only quickly motivated the rules for the connectives. Are the rules that I gave you correct? There are other choices for how to interpret them, and it would be good to have some principles guiding our choice of truth tables. Your answer to this question will depend on what you take the degrees of truth to really mean. What does it mean for something to be 50% true? It's not a matter of probability. These values have the same numbers as probability values, but they work very, very differently. How does something get the degree of truth that it has? This is related to our next question. One advantage in fuzzy logic is the absence of a sharp borderline between the red and the non-red, the young and the not young, etc. But if you look closely, you'll see that we've traded in one borderline for infinitely many. Now, along a strip of 10,000 colours evenly shading from red to yellow, there's a last patch which is red to degree 100%, and there'll be a first patch which is exactly 50% red, and so on. The choices for these patches are arbitrary. They don't seem objective. We've traded in one problematic boundary for many. This doesn't seem like an improvement. Finally, assigning numbers to truth degrees means that you can compare them when it doesn't seem to make sense to compare. Suppose you have a borderline case of red and a borderline case of large. Does it make sense to say that the circle is red to exactly the same degree that the circle is large? The degrees seem to be completely independent of each other. It's for reasons like this that some friends of fuzzy logic attempt to generalize their picture even further so that we still have degrees of truth, but they're more flexible and not just tied down to being numbers. I'm going to leave our exploration of fuzzy logic there. In our last lesson for this section, I'll take the other approach to our three options and see if there's some way that we can retain two-valued logic in the face of vagueness.